session for this course on microsensors and nanosensors. So we'll take, there are two different doubts. So we'll take those first in little detail, and then we'll talk about the different modules that we are covering in this live session. Okay. The first doubt is by some student where he or she has mentioned that in the given assignment 5 solution, answer for question 3 is B and D, but in the evaluation of the assignment, the answer for question 3 was A, B, and D. Please clarify. Okay. So the question is related to a SAW sensor, and the doubt, the option A was coming redundantly. It was not required. So the actual answer is B and D. We'll see SAW sensor in little detail once again, and we'll see that why answer A is not correct. Okay. So if you remember, the surface acoustic waves SAW were the sound waves, not the light waves. Okay, that travel along the surface of an elastic material. Okay, and for humidity sensor, this was kind of configuration where you have two interdistributed transducers. One is for the generation of the acoustic wave, and this was at the receiver side. Okay. The amplitude of this SAW wave decreases exponentially as they move into the material, confining them to a depth of around a wavelength. Okay. These signals were also known as relay waves, if you remember, and the relative humidity were determined by measuring the relative change in the phase velocity. Phase velocity and group velocity we have seen in little detail when we discuss the course. We'll revise it once more today. Okay. The relative change in the phase velocity and frequency were related by the expression this delta nu by delta nu by nu naught was very equal to delta f by f naught, where f is the frequency shift caused by the absorption of the humidity in the sensing material or the receptor, and f naught was the initial frequency. Okay, this actually relate to velocity delta v by v naught. Okay, delta v by v naught was the change in the SAW phase velocity and the actual SAW phase velocity. Okay, so this equation, if you remember, we have discussed to be equal to minus pi h v naught square by 2 lambda into this factor, which was mostly coming for the normalized displacement amplitude of the SAW. Okay. Phase velocity and all, I will not go in detail. We have talked about phase velocity and group velocity in detail. So coming back to the question again, the option A was light wave traveling along a metal surface. So option A is not correct. Actually, it was option B, which is sound wave traveling along the surface of an elastic material, and these waves are also known as relay waves. So option B and D are only the correct answer. Option A is not the correct answer. Okay. Then second question was, what is the result of piezoresistive sensors? Okay. Piezoresistive, I mean, when we discuss this topic in detail in our module 4 maybe, or module 8 maybe, or 7, where we talked about force sensors basically. So module 7, I think. Okay, so if you remember, piezoresistive force sensors we have talked in detail, where we have seen that the piezoresistive effect was a little different when you compare it with the piezoelectric effect, right? So piezoeffective effect, if you recall, generates charge or voltage, while the piezoresistive sensors were generating result in the form of change in the resistance. Okay, usually these piezoresistive devices are connected in Wheatstone bridge. So even the output is in the form of voltage. Sometimes it can be misleading. The result is mostly in the output of the piezoresistive sensor is basically in the form of change in the resistance. Okay, although as I have mentioned that when it is connected in the Wheatstone bridge configuration, you will find that output is in the form of voltage, but that is on top of the resistance factor that is coming from the piezoresistive device. So if you remember the working principle of piezoresistive force sensor, we had a force applied to a piezoresistive material, and the output was the variation in resistance, which was measured by some mean. Okay, and that's how you characterize a piezoresistive force sensor. So output was something like delta R by R is equal to the strain factor into the del L by L, which was the basically the strain. So del L is the length variation of the strain gauge due to deformation, while L is the length of strain gauge before actual deformation happened. Okay, so this is how the piezoresistive devices are characterized. They give you output in the form of change in the resistance. Okay, so let's see if we have some more questions. Then otherwise we'll discuss about the piezo, the other topics that are covered in this module. So in chat box, let me see if we have any questions. All right, so we do not have any question over here. So better I will continue my discussion on the topics that is of our interest in this module. Okay. Fine. So from week 4 to week 8, we have seen diversified topics. The week 4 is mostly dedicated to the interface circuit. Okay, and in the next module we have discussed about humidity and chemical sensors, and afterward we talked about temperature sensors, and then force sensors followed by tactile and pressure sensors. The pattern of this course is like all the modules carries nearly equal weightage. So in the module 4, where we talked about interface circuit, we have seen in detail that the sensors basically require a variety of interfacing circuit components for various purposes. We have amplifiers, excitation circuits, current to voltage or voltage to current or charge to voltage converters. Those things are required. ADCs and DACs are also required for data conversion, and then transmission, and then noise suppression strategies, right? We have discussed the op-amps in little detail. We have seen the properties of op-amp, including its high CMRR and the low intrinsic noise that is associated with op-amp. And we have seen this different configuration of op-amp, that how it can be utilized for using these properties, how this can be utilized for various circuit components which are more prominent for the sensing application. Okay, we have seen that a broad operating frequency range of these op-amps are very crucial in designing new interface circuits for sensors, and the low sensitivity to variations in the power supply voltage makes them optimal choice for the amplification circuits of the sensors. Okay. Their high environmental stability is very crucial for designing new interface circuit design components for these circuits. We have seen a number of configuration of these op-amps, including utilizing them for as a summing amplifier, or in designing a differentiator or integrator. Among them, we had a unique application of the op-amp as a voltage follower. In an electronic circuit provide impedance conversion from high to low level. Basically, it is a current amplifier and impedance converter. A typical voltage follower, as you can see, carries high input impedance and low output resistance. I hope that these topics are very much clear to you. You might have also studied these topics in some other subjects, but this is very important for this course also. Okay, we have seen that good voltage follower circuit has a voltage gain very close to unity, and very high current gain also. Okay, in the series we have seen a number of circuits, including excitation circuits, particularly for powering up the active sensors, and among them current generator or a current pump we have discussed in detail, which were the device which can produce electric current independent of their load impedance, right?
क्लिक करके जाना वो खत्म हो जाएगा उसका नहीं ये ऑनलाइन है
so
हाँ ये ऑनलाइन है
can you help me with
live session
I have done it. Okay, fine. Yeah, so I'm sorry for the interruption. Let us continue our discussion on current generators. We have seen that in this module, we have discussed in detail that how current generators can be designed and how they can be utilized for as a source for active sensors. Okay. Then in the next module, we talked about humidity and chemical sensing. We talked about the applications of humidity sensor, and we have seen that the application of humidity sensors are really broad, from industrial processing to its application in agriculture and utilization in the manufacturing sector, like in the manufacturing of integrated circuit and medical devices. So we have seen a whole lot of transduction technique which can be utilized for humidity sensing purposes. We have seen that capacitive sensor is the major, the majority of sensors in the market are basically based on capacitive technique. Okay. So all those techniques we have seen dominated by capacitive, but not limited to capacitive. We have seen based on interferometers and other optical techniques as well. Okay, for toxic gases, we have seen a number of transduction techniques, including the very basic chemiresistive devices and optical sensor, which are based on reflection, absorption, interferometry, and so other applications or other transduction techniques, right? So we have covered them in detail. We have also seen certain fabrication strategy to make these devices. So you can utilize the techniques that we have discussed in module 1 and module 2 for the fabrication. You can extend them to the gas sensor or miniaturized micro gas sensors that we have discussed in this module 5. Okay. For temperature sensor, we have talked in detail on both kind of temperature sensors, including contact temperature sensors and non-contact temperature sensors. For the contact temperature sensors, we have talked about our discussions were around the resistance temperature detectors, RTDs, thermistors, and thermocouples. For thermistors, we have seen different kind of thermistor, including NTC and PTC thermistors, and we have seen a number of equations that govern this thermistor, including there were certain modeled equations that can fit a different kind of thermistors. And for non-contact sensor, we have seen active and passive infrared sensors in detail. Okay. Then in force sensor, we talked about different class of force sensors, like force sensor based on strain gauge, based on piezoresistive, capacitive, and piezomagnetic techniques. We have seen that how these force sensors can be fabricated using MEMS technology, and I hope that you do not have any doubt in the fabrication flow of these force sensors. Okay. We have also talked about certain optical force sensors. These optical force sensors were again divided into different type, including the tweezer type optical force sensor, which were using a different kind of principle which we have not seen till this module. Okay. Then image-based or vision-based force sensors also was very important, and we have altogether seen a new class of polymer where we talked about electroactive force sensors. So I think that these topics you will cover in more detail when you prepare for the end sem exam of this course. Okay. Then we talked about tactile and pressure sensors. So we have seen a number of tactile sensors like touch, spatial, and slip kind of tactile sensors. And they were again based on a number of transduction technique, like based on resistive or in better sense we call it piezoresistive. Then we have seen capacitive, ultrasonic, magnetic, piezoelectric, that kind of devices. And then we also saw tunnel-based tactile sensor, which were very crucial for quantum devices. Okay. Pressure sensors we have seen in this module having two fundamental components for construction, like two important components that were required in this pressure sensor were the plate or membrane, which is having a certain area which were known, and then a detector that respond to the applied force. Okay. We have seen it based on diaphragm or based on plate or membrane, which get deformed under the pressure. And again, this is fabricated in a silicon based structure. Okay. We have seen number of transduction mechanisms again based on piezo, resistive, capacitive, piezoelectric, and optical. So this kind of plate or membrane-based pressure sensor were fabricated using the MEMS technology, and the Z max and sigma max we calculated as R square P by 4S, where S was the radial tension and R was the membrane radius. Okay, we calculated it for the plate also. The maximum deflection we calculated, and it was found to be relating to pressure linearly. And in this equation, a new term was coming, which was basically the material property or the Young's modulus of the plate was coming into picture because of its shear thickness. Okay, so we have also included the Poisson's equation, Poisson's ratio in this equation, where the Z max was calculated or derived to be 3 to 1 minus Poisson's ratio square into r to the power 4, which is basically the radius of this plate into the pressure divided by 16 into the Young's modulus into g to the power 3. Okay, so by this we have found that the maximum deflection is again, if you keep all these things constant, the Z max was again proportional to the applied pressure. Okay. So these were some crucial topics that we have covered in this 4 module, and I hope that you are able to execute the assignments that were given to you. Okay, so yeah, so that's all I just wanted to discuss with you. Okay, fine. If there are no more questions, I think we may leave the meeting, and I will request you that if you have any question, even beyond this session, you can put it on the portal, and we will be happy to take that in the next session. Even if you feel that that question is from module 1 or 2, and that particular session is already gone, but then also you can put those questions. We will definitely take them. The ultimate aim is that you should be benefited from the course. Okay, so I hope that. Yeah, so Mr. Malapati is, I think, there. Yeah, so let me unmute him.
Dr. George.
Hi, Malapati. Yes, yeah.
How are you?
I'm good. Yeah, if you have any question, please, you are welcome. Yeah.
The course is very nice, but bit difficult, exploring a lot of devices, sensing devices. My question is, is there any possibility of what kind of topics we have to focus on? Because the lectures, overall 12 weeks, huge lectures, So,
I can understand. Malapati, I will request that all the lectures carry equal weightage. Basically, okay.
Okay. Yeah.
But as you are already a known researcher in your area, what I will suggest that for benefit, particularly for the research purposes, what you can do is you can focus on the kind of device that you intend to utilize for your work.
Yes,
okay. Maybe since I have covered a plethora of devices in this course, what we can do is you can, for course you can prepare as per the guideline of NPTEL, but for any particular device that you want to work upon, okay, because this is although for undergrad course, but it also can be fundamental for someone's research. So if you feel that if you are interested in particular topic, I think that you go and deep dive into that particular topic, and we can explore that offline. Okay, we can talk about that particular device offline. Okay, that will be better.
Yes, yes, certainly. That is the aim of attending the course, of course.
Yeah. So that can be done.
That, venturing into particular devices where I can suited, with my backgrounds. Yeah.
True. So that will be better, because most of the devices are either physical devices or chemical devices. Of course, we have covered healthcare devices, so we have a lot of biosensors as well. But since you are a physicist, you may like to take up any physical device, physical sensor, so you can target something like that. Yeah.
Sure. Thank you.
Yeah. So all right then. So we will then close today's session, and I will request that you keep on posting questions so that we have a lot more things to discuss in the next session.